And we'll do HSO3 negative. And some of you might know already that's called bisulfite or hydrogen sulfite. But in this course, you will not be asked the nomenclature of inorganic molecules like that. So where do we start? We start with valence electrons. From our periodic table that we're given on the test, there's a big Roman numeral 1 in the column with hydrogen, meaning 1 valence electron. In the column with sulfur, there's 6, and oxygen's also in the same column. And this species has 3 of those, and 1 more electron because an anion has 1 extra valence electron over the neutral version of this molecule. So when we're said and done here, that's 4 times 6 if you look at it. That's 24, 26. So when we're done, we have to have 26 valence electrons. Now, looking at the textbook, it says avoid oxygen in the middle and avoid oxygen-oxygen bonds if at all possible. That clearly makes our best guess for a middle atom as sulfur. And it's surrounded by 3 O's. Textbook says to try to go symmetrically. And why did I not put the H in there? Because H has to stick off the end. Now, here's what I see a lot of students do, and I don't want to see this. Don't do it. They see the H beside the sulfur and they do this. Don't do this. It's wrong. Oh, no. You're not going to get any points. What you fail to realize is this is an oxyacid. So read the section in the textbook about oxyacids. In that section, they describe an oxyacid when it's listed like this. We'll always have the H in front, some atom next, followed by some number of oxygens. This could be charge or no charge, doesn't matter. When you have an oxyacid, the only reason it's an acid is because the H is very positive. H will not be very positive if bonded to sulfur. It will be positive when bonded to oxygen. And later on in chapter 4, you're going to learn that H positive ion is called a proton. Some of you know that already. It's fine if you don't. Pick one of the O's and put the H on it. So we've laid out our skeleton. We've kept in mind this is an oxyacid. I'm going to show step by step, following the order in the textbook. So we started here, laid out a skeleton, using a light pink to go from here. We did valence electrons to here. I'm going to go to here. And right now we've used each bond is 2 electrons. 2, 4, 6, 8 electrons. 26 minus 8. We have 18 to go. My strategy, personal strategy, is to put 18 electrons as lone pairs on the outside atoms, if I can get to 18. Right now I'm at 10. Didn't get to 18. 16. All the oxygens have full octets, and the sulfur doesn't. You can get a full octet by doing this. And you have to put 2 more on. Do not put 2 more on the hydrogen. Hydrogen, its nature is to have 1 bond, and that's the end of its story. Oxygen can never violate the octet rule, so you can't put more electrons around oxygens. Have to put the 2 electrons around sulfur. I hope those electrons are showing up okay. Well, my video viewers, are these lone pairs okay, or are they just too faint to see very well?
No, they're fine.
Okay, cool. All right, so that led to this structure. We're not done. We do have 26 valence electrons. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Formal charges are next. I think I'm going to get that little arrow. I didn't. May have missed a lone pair or two. Let's see. Let's see what we got. Nope, we got everything. Oh, not my intention. That's what I wanted. I'm going down here. Oxygen's formal charge. Here's the formal charge is electron ownership compared to the atom on the periodic table. Oxygen on the periodic table in group 6, Roman numeral VI, owns 6 valence electrons. This oxygen owns 7. Let me explain why. It owns each electron in the lone pairs, so 2, 4, 6, and it shares these 2, which is similar to owning 1. Sharing 2 electrons is like you own 1. So it owns 7 electrons. 6 plus 1 is 7. That oxygen has an anionic formal charge of -1. My personal preference is to circle those formal charges. You do not have to do so. This oxygen has exactly the same story. The oxygen over here, it owns 1, 2, 3, 4, and only half of this for 1 more, and half of this for 1 more. That's 6. No formal charge. You don't put anything on this oxygen. If you put a 0 there, it's not wrong, but you're wasting your time. You don't need to do it. Sulfur here owns both of those electrons, half of that, half of that, half of that. That's 5. On the periodic table, it owns 6. This sulfur owns 1 less valence electron than the periodic table. It has a +1 formal charge. And you haven't got your answer to A yet. We do not have the most stable resonance form. We've got all the octets full. Check. We have all the formal charges on. Check. Sulfur is not limited to the octet rule because it's in the 3rd row of the periodic table where d orbitals are available for making bonds. So to get formal charges lower, sulfur can make more bonds than it has here. And if you can move electrons towards the sulfur from a lone pair on one of the oxygens, by doing this, let's do the skeleton the same way. Well, I could save a lot of time just copy pasting, couldn't I? I'll probably get an arrow on the way or 2. I can live with that. I'm going to take this pair of electrons off. Now, when you do that, the charge is going to change. We'll evaluate after we're finished. Now you got to put the pair of electrons back on, and you got to make sure oxygen still has a full octet. You're allowed to make a pi bond where you used to have only the sigma. There's the pair of electrons. It came back. It came back as a bond, a pi bond, instead of being a lone pair. And do the calculation here, and you've got 2 improvements, don't you? In fact, you've done enough improvements to call it the best Lewis structure possible. Let's see. Oxygen owns 1, 2, 3, 4. Half of that is 6. That's 0 because oxygen's in group 6. Same story for sulfur. It owns both of those, 2. Half of that, half of that, half of that. Yep, that's 2 bonds. It owns 2 electrons for those. Half, 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 half is 1, 2, 3, 4. And that's 4 more plus 2 is 6. So 0 formal charge. Now, in this molecule, you know you have to have at least 1 formal charge when you're done, right? Because there's a formal charge in the ion. And this is the best Lewis structure. So this is the answer to A. And I just realized you draw an alternate resonance form. Explain why your first structure was minus stable or tied. I have to edit this. All right. And that's A. And I'm going to go to B. Draw the resonance form. And that O here can resonate its lone pair that used to be this lone pair. And I'm going to show in the bonus that lone pair there was used to make a pi here. You want to be consistent and make a pink pi? Why not? And the oxygen on top has 3 lone pairs again. Sulfur didn't change its lone pair situation. This oxygen didn't change. This is a tie. Don't forget the formal charge. On the top, oxygen is minus. And both of these structures have an anion on oxygen, so there's not one advantage of one over the other. They both have sulfur double bonded to the other oxygen. And the bonus would get this. Here's the bonus. Yeah, let's do it in a different color. Bonus in purple. No, that's not purple. Purple's kind of close to blue. Hope it provides enough contrast here. This is called resonance. That's how it happens. The lone pair resonated in to make a pi bond. That's where this pair of electrons came from. The old pi resonated to the oxygen and became a lone pair. That's where this lone pair came from. And there's a tie. There's another resonance form. So this would be B. And not asked for here, but good for educational purposes. Tell me what you would get if you resonated this lone pair and then dump the lone pair back on the O here. And that should have been in purple, just to be consistent. Hey, you get more practice. And we're going to explain in the final moments of this little segment why this last one is not as good as the previous two. No, that's just wrong. We do not transmute elements to other elements. And maybe you can help me out. So I got yeah, go ahead, Hassan.
So then that one wouldn't be the most stable because oxygen's not where it likes to be because it has 3 bonds and only one lone.
That's right. And because of that, it has a formal charge too, right? We'll work it out together right now. We've got oxygen owns both of those, and half, half, half. That's 2, 3, 4, 5 plus 1. Oxygen is notorious for not liking being positive. And the sulfur is still neutral, but we'd have to, if we had to explain, we just say too many formal charges. Too many formal charges.
So if you were to ask a question like this on the test, and then, so if we were just to say something about how oxygen's not at where it would want to be, basically at the 2.
Now you'd have to give me a little more. Explain why it's not where it wants to be. I'm just trying to make this very clear that this structure is going to spend almost no time like this and almost all of its time like this, and these are 50-50. This structure is going to spend 50% of its time like this, 50% of its time like that. And when you have 4 formal charges versus 1, and none of them are very big, they're all unitary charges like -1, right? And -1 and -1 and +1. So the biggest factor is if they're not, like a -2 is like Haram. You don't do a -2 if you can get away from it. All right. Well, that's not even an issue here. They're all single charges, but this one has only one single charge and this one has 4. So this one's a lot better than that.
Okay, so it's basically because of the formal charges, not because
Yeah,
of
just
like.
the number of formal charges here. Now, as you're reading the book, you'll see examples where what comes to mind in the text, just quickly here, we had a popular ion here, SCN, with this Lewis structure. Oops, don't try to put the minus over where it belongs. And resonating away. This is for thiocyanate. Resonating away. It's going to spend a lot more time like this, not as exaggerated as the previous example. And this. And in your explanation, I don't want to hear about double versus triple bonds. No, that's not what this is about. In the 2 examples of the resonance forms, the formal charge is the least stable part on both of these. Charges are the least stable parts of ions. A more negative nitrogen brings the electrons that contribute towards the formal charge closer to the nucleus, which makes them more stable. The less electronegative sulfur, of course, you've memorized your electronegativities, right? Sulfur and carbon and iodine are all 2.5 CSI. That's not, those electrons in the anion are less close to the sulfur nucleus than the electronegativity 3.0 atom nitrogen, bringing these closer to the nucleus. So I'll write that down. More electronegative N, electroneg N stabilizes minus better than S. And right there, I think we have a usable segment for a Q&A video. Does anybody have a question about what we just did? Or
So,
need?
Professor,
Yeah. Mm-hmm.
so since the more electronegative is better with the negatives, right?
Mm-hmm.
With like the
Absolutely.
would the less electronegative be better if there was like a positive on it? You know what I mean?
Absolutely. Yes. If you had to choose between a cation on nitrogen or a cation on carbon, you prefer the carbon because remember, electronegative atoms bring things close to the nucleus. So do you want to bring a positive charge closer to the nucleus? Think about it. What's the nucleus's charge? Positive. Do you want to have positive close to positive? No. So yes, your argument is holds true for reversing the sentence. A less electronegative atom would stabilize a plus better than a more electronegative atom. Okay.
Okay.
So good question. All right. Call that a segment. I'm going to come back. We can discuss and maybe do another one or maybe call it a day. We'll see. But you'll just have to wait about 5 minutes and I'll see you then.